really work? It doesn't seem to work. Yeah, I want to have the same unknowns both inside and outside the integral. So I think I can do that. I can do that. I think we should end one. I can do that by applying the n dot grad operator. Is equal to minus the s prime c1 g1 r prime. And then I have the same set of unknowns both inside and outside the integral. I can convert this into an integral equation that I can solve. There's one way to do that. Another way I thought I can apply the extinction theorem. Force this to be 0 by the extinction theorem. Yes?
How does the n dot that operator not act on the integral?
Oh yeah, you're right. You should add on this one as well. Okay, you should add on that. So I will have this integral equation to solve. Or I can impose the fact that I have the boundary condition that that surface is a pressure release surface, is a soft surface, and bring this to the surface and force this to be 0. G of r prime is equal to 0. Then I have only one unknown, one set of unknowns. And then I can solve this problem as well. Okay? So I essentially have a problem that is rather simple looking, that looks something like this. A incident of R is equal to ES, some kind of a surface source that can be monolayer source G of R prime. So this is actually very similar to an electrostatic problem that I posed to you before. You let sigma of R be equal to a set of basis functions, and then after you substitute in, you test it with another set of basis functions. You get this equation at the final n. You get this equation at the final n. N is to the 1 to n, a n, w n, g r prime, sigma n. Okay, you get this. And this means an integral. Whenever I put a comma, I mean an integral. Okay, I can convert this into a matrix equation. This could be the matrix A m n. This could be the vector B m. I have a matrix system to solve. Okay. And what you notice is that in this matrix system, I will expand my unknown sigma n as surface charges, surface sources, monolayer sources. I can break the surface into finite elements and then put this sigma n on the surface. And then I will compute the field due to these basis functions. And when I test, no matter where I test, okay, this might be R prime. No matter where I test, this element is non-zero because this is a Green's function. Green's function is all pervasive. The Green's function is everywhere. It's everywhere, right? It's all pervasive. It's always non-zero everywhere. So this thing is always non-zero no matter how far M and N are, no matter how far these basis functions are. So this is essentially a dense matrix system. And so we have a dense matrix system to solve. A dot A is equal to B, where this is dense. And this is essentially the shortcoming of an integral equation method. The matrix system is dense. Whereas if you do finite element or you do FDTD, the matrix system is sparse. Okay, the matrix system is sparse. So what do we need to do? Dense matrix system is very expensive to solve. If you invert this system, if this A is small, you can always do this. The cost of this is order n cubed. This means order n cubed. If this is n by n system, it costs that much cost to solve this thing. You can also solve it iteratively. You can, say, perform a very simple iteration technique, is just to do this. You can say that the matrix A is the diagonal part plus the off-diagonal part. This is the diagonal part. This is off-diagonal part. So the matrix A is a dense matrix. It will look something like this. Everywhere be non-zero. Okay? But I argue that the diagonal part corresponds to R and R prime very close to each other, or the testing and the expansion functions on the same element. I argue that the Green's function is largest over there, and hence this element is the largest. So I can argue that this term is usually quite large, because it represents the diagonal elements. This term is somewhat smaller than this term. So I can write that equation as B plus T dot A is equal to B. Then I can say that T dot A is equal to B minus B dot A, right? And then I can multiply it by B inverse. B is diagonal, so I can find its inverse very easily. B inverse dot B is minus A, right? So I can use this to iterate. I can find an plus 1 from an. I assume that after I found the solution by ignoring D, is that right? Ignoring B, okay. I can ignore, am I right to say that? No, I can, first I can ignore T. Assume T is equal to 0. If T is equal to 0, P is a non-diagonal part. Let's assume that it's 0. Then A is approximately equal to B inverse dot B. So you can think of that as an approximate solution of that equation if T is not there. And AN would have been equal to that if T had been 0. But if T had not been 0, I should add this correction. Okay? So this is the simple iterative solution to solving this problem. Yes?
Why can't you say an plus 1 will be equal to D inverse B minus B inverse D in n? Why are you choosing an plus 1 here?
Oh, because I want to make this to be the zeroth order solution. I know that when T is small, only the diagonal term dominates. And the approximate solution should be given by this. If T is small. So if I write my solution in this way, okay, it says that if T had been small, my solution would be that this is equal to that. Okay, but this gives me a correction. Correction to my an plus 1. Okay, you can also think of this as, if you write it in this manner, I plus D inverse dot T dot A is equal to D inverse dot T. You can also write it in this manner, right? And if this is small, I just get the correction. I get this is my leading order solution. If this is not small, I should find its correction iteratively. Okay, this is another way of thinking of an iterative solver, but this is a very, very, very simple one. There are many, many, many things out there that gives you. Yes?
Well, like the T is still dense, right?
T is still dense.
Well, so it's still hard to solve.
It's still hard to perform this
Yeah.
operation. So you need fast multipole. Okay, we need fast multipole to perform T dot A. T dot A is still expensive. It's still dense because this is still with non-zero. So we need fast multipole to actually perform this. So the key idea of fast multipole is the fast multipole method. Okay. Or maybe just fast methods in general. You have a dense matrix system T dot A. This is order n squared cost. If this is a dense matrix system, the n squared elements altogether, the cost of a matrix vector multiplied, or matrix vector product is order n squared. How can we reduce this to order n to the 1.5, order n to the 1.33, order n log n, or order n? How can we keep reducing this cost? Okay, that's the essence of the fast method. And once you have figured out how to reduce this cost, then you can solve this problem many, many times faster. And the naive method, this is the naive. Okay, maybe it's called the double line. Naive method. Okay. So next lecture I will teach you how to do this fast. How to do this matrix vector product fast. Okay, using clever method. As a simple thing, the essence is that if you have a dense matrix over here, let's say it's AS submatrix dot A is equal to C. Essentially, how do I perform this matrix vector product fast? One simple way is just to do a low rank approximation. To write this as maybe maybe B transpose dot some singular value and W. You might be able to decompose this matrix in this manner. And if this is small, the cost of this is n squared. If you can do singular values so that this is small, so that this is might be m by n, this is n by m, this is n by m. Okay. Then the cost of this is mn in the first stage, m squared in the second stage, nm in the third stage. So the total cost is order n m. So you can do singular value decomposition so that n is a lot less than n. This can be much, much less than n squared. This is one simple way of finding fast methods. Doing low rank approximation or singular value decomposition and so on, but then there are other methods. Most of these low rank approximations and singular value decomposition work only for electrostatic problems. They don't work for electrodynamic problems. The fast multipole method and the multi-level fast multipole method will work well even for dynamic problems. Okay, we can talk about that next time. Okay, any questions? Yes.
So when do you get, in general, when do you get a small off-diagonal term? Is it when the frequency is high, or can we say that?
Usually, you do matrix partitioning. You break the matrix into many sub-matrices. Okay. Instead of doing a matrix vector product, you do a whole bunch of block matrix vector product. And then when you perform every block matrix vector product in a sequential fashion, many of these off-diagonal terms are low rank. Because they are low rank, you can use this kind of technique to speed up the matrix vector product concerning this block. This will be full rank. Those are on the diagonal, have very strong diagonal terms. They are almost like an identity matrix. Identity matrix cannot be reduced in their ranks. So this one you have to do by the conventional means, but they are order n of this, right? But there are only a small number of, there are many off-diagonal terms, order n square off-diagonal terms. So you can reduce the cost of the off-diagonal terms, you can speed up the algorithm. That's the essence behind the low rank factorization and low rank approximations. Okay. We'll talk more about that in the next lecture.
Yeah, that's